is Alexei Мячин, our associate professor of our department and senior researcher in our Center of Decision Choice and Analysis. And she will give us these very new results in pattern analysis. Alexei, please, floor is yours. Go ahead.
So today, good morning, everybody. Today I will present the results of my research, which is called Theoretical Aspects and Practical Application of Pattern Analysis. At first, we will have a little introduction.
Alexei, sorry, make it full screen mode.
Sorry. Just one moment. Can you see a full screen now?
Yes, yes, thanks.
Thank you. So at first, a little introduction about what is pattern analysis about, in which cases we can use pattern analysis. Then a little presentation about new methods, which we discuss in our laboratory of in our International Center of Decision Choice and Analysis, and in Russian Academy of Science. So a little introduction. These are the result of global overview report. So as you can see, as a result of January 2024, we can see then we have more than 5 billion individual using of the internet. We know then is about 2/3 of the total population of the Earth. We know then the increasing of each year is about 2, 3, sometimes 4% of the using internets. And we know then the average daily time spent using the internet by each internet user is about 7 hours. So it's too much. Using a lot of internet traffic, we can collect a lot of data. Actually, if we use some results of Internet Live Stats, for example, we can see then it's about 200,000 million emails in each day. So we have a lot of data to analyze. And of course, the interest, I'm so sorry. The interest of analyzing data now is very high. There are a lot of papers about that, and there are a lot of methods. How can we analyze big data? If we talk about class and machine learning methods, we can separate these methods using actually different methods. But one of the most popular is divided to supervised and unsupervised methods. Supervised methods are when data is characterized or numerical. The most popular is classification and regression methods. For classification, we have some predictor and the category, and we can divide by these categories. But the most important thing, and we can divide our data for data using of which we can create a model, and data using of which we can have a test of these models. And regression data, when we need to predict just a number. About regression data, regression methods we will not talk today, just about classifications, clustering, and pattern analysis. So the second part is unsupervised methods, where we have data is not labeled in any way. So at first we don't know how can we divide data. So we need to use a method to understand is this method good or not. About good or not, we will discuss today. The most popular methods are clustering, when we divide by similarity, for example, cosine similarity, Euclidean similarity, Manhattan similarity, Jaccard similarity, and etc. Association methods, when we can identify sequence. And one more method is dimensional reduction. So of course, when we have a lot of data, we need to do something with that. So we need to create some methods which can reduce our data. So, and one more type of methods which we want to discuss today is pattern analysis. Pattern analysis is some methods which are unsupervised too, so data is not labeled in any way. We cannot separate our data for construct some trained data and test data, but we need to have some results. And we divide by similarity too, like clustering, but there's some difference. Actually, if we see the results of Google Scholar, I checked these results yesterday. We can see that there are a lot of interesting about papers in papers was about dividing separate some data with groups. The results about machine learning is actually about 6 million for today. But actually, if we compare with classifications methods, clustering methods, and pattern analysis, the results about pattern analysis about 10 million results for yesterday, actually. So what's the difference between pattern analysis and clustering? I'm sorry, at first let's discuss classification methods about the difference between classification, clustering, and pattern analysis. Sorry. So for classification method, we have some trained data, we have some test data, and our main idea is create some function in the biggest part of case, which can actually separate this data. But for construct this type of function, we actually know the results of train and test data. So we have some trained data using of which we create this model. So then we see if this model good for us or bad using some metrics, and then check in our test data. In the biggest part of case, we divide by 2/3 and 1/3. And in these 2/3, which we for trained data, we divide by 5 parts. It's called cross-validation. These methods are really used for today. For example, this example for 2019, I saw this example at first of all in some conference of data mining in New York. So some professor discussed the result of some methods of classification data, and he proposed this example. Then if we construct some method of classification to try to find using some pictures long-termer and compare the results of professional doctors and the results of this machine, so the results of this method of classification. We can see that the result of the computer, so the methods of classification, which he discussed, is better. So now actually the results for 2019 is about 0.3. Now this results about 0.56. So now it's better too. And for doctors for 2019, the detection is just 2 of 15. So as we can see, the result of classification was better on these days. When we talk about classification methods, sometimes we talk about some special methods of create some function using some weights of the parameters. This method is called neural networks. I propose just some very small example. I will not demonstrate today, but if it's interesting for you, you can use, for example, for demonstrate for students how neural network works using this very popular example with the library TensorFlow of Python, which propose some to check how different neural networks works. So classification, we have trained data. For clustering, we don't have any trained data. We don't have any test data. We cannot divide, but we need to construct some function, use some metrics to separate that. We can use it in different ways. For example, one of the most, I think the most popular methods, the most famous method of clustering is k-means, when we propose some centroids of the each cluster, this group of objects, and we evaluate the distance between the centroid and each object. And we need to construct some model using of which the distance between the centroids and the average distance between centroids and all objects included in this group of objects, also in this cluster, is very small, and the distance of different clusters are bigger. So when we discuss about, we have a discussion about different methods, we need to understand what is, so we have different methods, which methods we need to use in each case, and what is, can we construct actually some best method using of which we can use in any case. So, and using of which we don't need to construct some different methods, so construct some new methods. We can use just this type of methods. So actually, one of the first paper when proposed the discussion about different methods of clusterization is some paper for 1966 published in Paper Recognition. This is called Clustering Techniques Using Dilemma, when they propose just 15 points. So just data which discussed nothing, just 15 points. And they propose different methods, a biggest part of which is not used now because the complexity of this method is too high. And then they asked the very simple question: what is the best division of the data using clustering and analysis? Now, so we have 7 methods, 7 different results. And can we understand what is the best method, best result here? Actually, in 2005, in another paper, they proposed the same question. And actually, about 20 years ago, there was created the impossible theorem, it's called, using of which we can have the same answer. The answer is, of course, no. In different case, we need to use different methods. And the most important, of course, we have some metrics for understand if this method good or not. For example, we can use some method basic of cosine distance, some methods basic on Euclidean distance, and construct some metrics for understand if this result good or not. But the most important thing is always the interpretation of the data. For example, here we have the result of different methods too for 4 different data sets. And in each column, we have the result of different methods. And as we can see, in the first line, we need to separate our data for 2 subsets, the small circle, the big circle. In the second line, 2 subsets too. In the third line, for 3 subsets. And actually, in the last line, actually, it's a big question, how can we separate this data? But the answer for this is some classical data for train, and compare different methods. The answer here is we need to construct just one group, one cluster. And as we can see, for example, 1, 2, 3, 4, 5, 6. In the line number 7, we can have really good result. But in this case, we cannot have some interpretation of this data. So the most important thing is, can we have the interpretation or not? This is another example where we can have the interpretation, and using different methods, we can separate this a group of animals by different clusters. But the question is, we can use, of course, different lines, different functions for that, different methods. But what is the result which we need? For example, we can separate something like that and divide by predators and non-predators. We can separate something like that. We can separate, but each group, for example, for fox, lions, tigers, zebras, and etc. And the question is, in this case, is the result good or not? If it's not, we actually can use another method. If the metric is not very good, but we have good interpretation, actually, the better is use good interpretation. So this was a little introduction. Sorry. So let's discuss pattern analysis. What is pattern analysis about? Pattern analysis is some unsupervised method, group of methods, in which we don't have train data, we don't have test data, and we need to separate our initial set of objects, each of which are represented by some features, by some groups. Our groups in pattern analysis are called patterns, using some metric. So it looks like it's very similar with clustering, where we divide by clusters using some metric too. But the difference is, in pattern analysis, we need to use ordinal scales. What does it mean? I will represent this idea in a very simple example. For example, we study some regions, 5 regions, by just 3 features. Let's imagine that all data is good. We don't need to normalize this data. We don't have some missing of this data. So complete data, we need to separate by groups. Let's try to visualize this data. For visualize multidimensional data, there are a lot of methods, of course. For example, web diagrams is very popular in humanitarian disciplines. But for pattern analysis, the most popular methods is to use parallel coordinates. So we have parallel axes, each of which represents some parameter. In each x, we add some point, the actual value of the parameter or normalized value of some parameter, and construct some piecewise linear function. Each piecewise linear function represents each object. One piecewise linear function, one object. And we need to construct some method which separate similar objects. But we need to discuss what is similar. Of course, using different metrics of similarity, we'll have different results. But just looking at this simple example, hypothetical example, we can see, okay, regions 1 and 2, the blue one and the green one, looks like very similar. Regions 4 and 5 look similar too. The results are very close. And region 3 is not very similar, so we need to construct 3 groups. And actually, using the methods of cluster analysis, of course, it depends of which method do you use, which metrics do you use, but using the biggest part of this method, for clustering analysis, we will have the result. Regions 1 and 2 are one cluster, the results of the values of which are very similar. Regions 4 and 5, second cluster, and region 3, the third cluster. This is the result of clustering. But for pattern analysis, we will have really different result. Let's see. For example, if we see the result, the features of region 4, we have the parameters 9, 5, and 8, and just multiply it by 5, we will have actually the features of the result of features of region 1, 45, 25, and 40. The same for region 3 and 5. For region 5, we multiply by 5 each result, and we'll have the results of region 3, 25, 55, and 25. So as we can see, this structure of regions 1 and regions 4 are really similar. Actually, we have the same result, but we just need to multiply each numbers of region 4 by 5. The same for region 3 and 5. So for clustering, we have 3 clusters here, region 1 and 2, first clustering, region 4 and 5, second one, region 3, the last cluster. But for pattern analysis, it's important this structure of each, in this case, region. So for pattern analysis, we will have the result. Regions 1, 2, and 5 will be in one cluster. But, sorry, in pattern analysis, it's called not clusters, patterns, of course. Regions 1, 2, and 4 in one pattern, regions 5 and 3 for the second pattern. So for pattern analysis, it's not important the absolute values of parameters, just the structure. If in your case it's important just the distance between some parameters, so the absolute value of parameters, is better to use clustering. In some case, for example, if we want to separate big regions and small regions, for example, we can use clustering. Big bank branch and a small one, we can use clustering. But if we want to understand the structure, we can combine, in this case, regions with really different values of the parameters. So the difference of these parameters is big, but the structure is really similar. We use pattern analysis. This is the difference between these two methods. So for pattern analysis, actually, for visualization of patterns, actually we have some problem. This problem is discussed, started to discuss in 1995 in the work about parallel coordinates. So the problem is if we change the axis, for example, we can use some method which is correct, but the similarity changes. For example, if we use ABC, maybe this, in this case, banks are similar. But if we change the order of the parameters, so we can see, so looks not very similar. So, and the first question is, will the result change if we change the order of parameters? Of course, the answer needs to be no. We can use any order of the parameters. The results don't need, result will not change. In 2008, there one popular paper and proposed, okay, let's use just compare the initial order, the inverse order of ABC, CBA, and let's compare in this case the results. Of course, the results will be the same, so we don't need to study any another order. The problem on study all orders, of course, for n parameters, we will need to study n factorial orders. So the number of permutations as n factorial. So the complexity will be really higher for a lot of parameters. So we proposed some different methods of pattern analysis, the result of which doesn't depend on the order of the parameters, of course. And then let's talk about the practical applications of these methods. The first two methods which we proposed is called ordinal fixed on the left side and ordinal invariant, a little bit more popular on the right side on the slide. So how can we use these methods and what this method is about? So we study some set of objects if each is represented by some features. For ordinal fixed, we use for have some first results. So these results will be very fast, and we can compare very fast for different methods. So we need to use the pair comparison of each parameter in the initial order. Using the result of pair comparison, we compare more, equal, and less. We construct some code. For code, we can use any numbers, for example, 1, 0, 2, and construct some code using this order of the parameters. Then we need, for each object, we have each codes, and we need to evaluate the Hamming distance between each codes of the parameters. If the Hamming distance equals 0, we combine these objects by one pattern. This is step 1 for ordinal fixed pattern clustering. Then we use ordinal invariant. For ordinal invariant, of course, for ordinal fixed, we have the problem, then we can change the order of the parameters. But the result will be the same because we have the pair comparison, more, equal, or less. But the visualization can be not equal. So we use the second one, ordinal invariant. For ordinal invariant, each object is represented by a full directed graph, where the vertex are actually just the value of the parameters, and the edges the result of pair comparison. We know then it's full directed graph, so for n primes we need to use n by n minus 1 over 2 comparison, results of pair comparison, and using this full directed result of pair comparison, this full directed graphs, we construct some new codes of each object. And using the result, the comparison of this result, the Hamming distance actually between these codes, we try to combine each object for groups, for patterns. If the Hamming distance equals 0, we combine. If not, we separate. So looks very simple, but for these methods, we have really good basic properties, using of which we can work with big data. So, of course, the first objects, the first property is if we construct some groups of objects using these methods, this group of objects, these patterns do not intersect, of course, because we use just codes. But the second property is actually more important. If there exists a sequence of indicators in which the values form and this strictly monotonically increasing or decreasing, of course, sequence for each object of the original set X, then this is an ordinal invariant pattern clustering, or some pattern which is constructed with ordinal invariant pattern clustering. Why is this property important to us? Two main things. The first one, for example, we need to understand starting of which step or starting of which pair comparison of the features the patterns or some objects in different patterns start to be different. Of course, in the first case, in the up picture, we can see, okay, it's not, maybe not too obviously, how can we understand? But if we construct some increasing, monotonic increasing or decreasing function, we can understand. So the difference is just between the comparison of parameters D and A. So if, for example, these piecewise linear functions represent different regions or banks or something like that, and we want to understand the difference will be just between these parameters, the main difference. And the second, we can use the second property for discuss one one more very important thing. There is an order of indicators for objects of ordinary invariant pattern cluster in which the values are monotonous, non-decreasing or non-increasing sequence for each object. What is this important? Let's see an example. For example, we construct some increasing piecewise linear function, and if we can construct the same for the same order, of course, of features, then these objects we can combine for one ordinal invariant pattern cluster. Why is that? Why is that important? Because if we construct just increasing or decreasing piecewise linear function, we can use, of course, sorting algorithms. We know so in the best case, the complexity of sorting algorithms is n log m, so it's really fast. If we can use sorting algorithms for create patterns, we can work actually with very big data. So in this case, this is very important to us. And the second thing is important too. For example, we don't want to analyze all data. We just want to find some pattern, some group of objects in which we can include some pattern. So we know some typical pattern which we can, using which we want to find some objects which are similar with this one. In classical case, what do we need to do? We need to study all data, then separate some data with some clusters, with some patterns, with some classes. For example, if we have classification methods. And then we need to see in which pattern cluster class is including this object. But if we can use ordinal interval pattern cluster and these properties of ordinal interval pattern cluster, we can just construct some algorithm which we say, okay, find just objects looking like that, some increasing or decreasing function. And we don't need to analyze all data actually. We don't need to separate all data by groups. We can just find objects for which construct these increasing or decreasing piecewise linear functions. And the third method, which we want to discuss today, is diffusion invariant pattern clustering. For example, if we separate our data by groups, and we say, okay, actually, we found some data which are structurally similar, but now I want to separate this data too for using absolute values of parameters. For that, we constructing diffusion invariant pattern clustering. How can we use and what is diffusion invariant pattern clustering about? So at first, we need to use ordinal invariant pattern clustering, separate by groups. And then for understand, are some objects similar or not, we need to change each value, the first value of the parameters by objects included in one pattern, the second value, the third, and etc. And then construct new codes using the same schema as ordinal invariant pattern clustering. And then compare the Hamming distance between constructed codes. And actually, we have the same principle. If the Hamming distance equals 0, we combine objects in groups. If not, we separate by different groups. Groups based on diffusion invariant pattern clustering are called diffusion invariant pattern clusters. For example, we constructed some pattern like that in the app. And we can see, of course, the parameter 4 is a little bit different between. So we have two objects with this parameter a little bit lower than all another one. And we want to automatically separate that. For cases like that, we can use diffusion invariant pattern clustering. For this method, we have really important properties, using of which we can compare diffusion interval pattern cluster, diffusion invariant pattern clustering, for another methods of clustering. This is the theorem. For example, we have two objects, for example, x1 and x2, described by some features, some vectors of features. And respectively belong to the same Euclidean cluster distance. So we have some distance, we evaluate the distance between these objects, Euclidean distance, of course, and between this object and the center of this cluster, like in King's, which we discussed, method we discussed before, described by some vector. And we know the radius R of this cluster. If we form some new objects, exchanging the corresponding values of one of the coordinates, the same as we do in diffusion invariant pattern cluster. So we change just one parameter, the first, the second, etc. For example, in this case, the first one. Then we can say that the Euclidean distance between the original objects and newly formed objects are equal, of course. But the second one is most important, is at least one of the newly formed objects belong to this new class, these clusters. Not both of them, at least one of them belongs on this cluster. Cluster, I mean diffusion interval pattern cluster. So why, in which another case we need to use diffusion invariant pattern cluster and actually methods of pattern analysis based off pair comparison of parameters. This is a very famous phrase for the handbook of Demidovich and Marian, Fundamentals of Computational Mathematics. In Russian, it's very good handbook. For example, we used this handbook when I was a student. We studied for this handbook. And it's called an, in most cases, calculations are made with approximate numbers and more approximately. Therefore, even for the exact methods of solving the problem, at each stage of the calculation, an error of actions and rounding errors arise. Under adverse circumstances, the total error can be so great that the result obtained will have only an illusory value. So, what does it mean? We can use correct data, we can use correct methods, and we will have not very good results. What can we do in these cases? I will represent this idea in some some famous classic test data for methods of clustering, classification, neural networks, pattern analysis. For when we create some new methods, we always need to test in some classical data. This is some classical data. Why it's called Wine data set, and I will represent this idea in this famous data. What is Wine data set about? So this is we have some parameters of wine, and we need to separate by 3 types of this wine. For divide by types, for by in which is a region of this wine. And if we use the visualization of this data in parallel coordinates and then separate by groups, we can say, okay, they are not so similar. So this is a little bit difficult to separate all this data. If you use pattern analysis, we use clustering, we use classification methods, the results will be not 100% good. But what can we do in pattern analysis? We can use the correction using centroids, like in k-means. What does it mean? We use one of the methods of pattern analysis, which we discussed before. Then what can we do? We can construct the centroid of each pattern and then evaluate the distance, Euclidean distance, between each objects and the centroids of these new clusters. So we use pattern analysis in this case for understand what is the centroid, initial centroid, and then correct the result. And actually, if you use methods like that, for example, in my data set, we will have just about 2% of mistakes. So it's really, really good result of this type of data. Another type of classical data. Oh, I'm sorry. Can you see the presentation now? Okay, I think you can see the presentation. So, yeah, thank you very much. So, sorry, let's continue. So, The second type of test data, which I want to discuss, is some iris data, very famous test data. I think the most famous test data in machine learning. The first data which all students discuss when we start studying machine learning is iris data. So we have just 4 parameters. We have 150 objects, which we need to divide by 3 type of iris. As I remember correctly, is iris Setosa, Virginica, and scalar. And why these methods are, why this data are is so popular? This is one of the first proposed data like that. It was proposed in a very famous paper in 1936, but is really hard to have 100% good result. So all methods have some mistakes in this data. And the problem is, for example, objects like on the left part, we need to separate, or not separate, sorry, combine, it's the same type, but on the right side, object like that, we need to separate. So as you can see, they're very similar, so we cannot construct some methods. It's really difficult to construct some methods which have 100% good result. For example, if you use k-means, on the left side, we can see the result. If we actually add 3 clusters, because if, for example, we just use k-means with random initialization or k-means plus initialization, we need to add the number of clusters equal 3, because in the biggest part of case, if we use, for example, some metrics like Scholarite scores, they propose just 2 clusters, the best result. But if we add 3 clusters, we say that we know the result is 3. We can see on the left side the result of k-means and the actual result which we need on the right side. As you can see, is really different. This is the result of one of the proposed methods, the result of ordinal invariant pattern clustering. And we can see then we have just 5 mistakes. Actually, if we use centroids, we will have just 4 mistakes. Not really better, but a little bit better. So the result of 3% of mistakes is actually very good on this data, of course. We tested in some more test data, very famous test data tool and balance scale data set. Is modeled for some psychological experiments and contain about 600 lines, 125, as you can see. And we have just 5 indicators, which characterize the indicators of the state of level weights for balance scale. And the first indicator is balance, left, right, left side, right side, characterize the state of these weights. And the question when they use some test data like that is, can we construct some methods which represent the result? Balance, left side, right side. And actually, if we just demonstrate this data in parallel coordinates, actually we can see then the results is really similar. So we don't need to use some difficult methods here. We can use just methods of pattern analysis. And as you can see, the result of pair comparison of each parameters will be really good for us. So in this case, we can actually use Hamming distance. The result is about 1% of mistakes. So really good. And let's discuss one more methods, and then let's see in which practical case we can actually use this method. So when we discussed at first this method in some seminar in Moscow, somebody asked, can we use these methods on interval data? Because actually there are some methods of construct groups using interval data, but they are not really good in all possible cases. And for patterns, we actually didn't find some methods of using interval pattern analysis, not clustering, not neural networks, not classification, pattern analysis using interval data. So we propose based on ordinal invariant pattern clustering, construct some methods which we can actually use using interval data. actually very similar with ordinal invariant, but the main idea here is it's difficult to compare interval data. So if for ordinal invariant we say if the first one is more than second one, less and equal, we add some number, so we construct some code. In this case, how can we construct this code? So we actually use the main idea of interval borders rule. The main idea here is if the intervals are intersect, we cannot compare them. So we use the code 0 in this case. If one interval dominates another one, what does it mean dominates? The left side of one interval is more than the right side of another one. So dominates is more than another one. So we can say that is more. In the next case is less. So we use the same codes 2, 1, and 0. Using these codes, we can construct some code of each object, and then we need to compare the Hamming distance between different codes or codes of different objects. And the same scheme. So if the Hamming distance equals 0, we combine them. If not, we divide. So in this case, the problem is we cannot use some sorting algorithms. We will have some problems, of course, for sorting data. So we cannot use the complexity n log m, but for m objects and n parameters, as you can see, the complexity is not so big. It's m cubed and squared over 4, so divided by 4. So is bigger than ordinal invariant pattern clustering, but we can actually use it too in some not very large data, but for some large data we can use it too. So, but can we reduce this complexity? Of course, we can reduce using some properties. Actually, the second property we can use. All indicators of objects belonging to the same ordinal interval clustering can be ordered in a consistent manner according to these rules. Compare more, equal, and less. These orders will be different for various ordinal interval pattern clusterings. So in this case, using this property, it's not always possible to understand can we combine the objects, but we can always understand can we separate these objects. So we can actually reduce the complexity of this method for using large data. This is some very simple example. We constructed some. Actually, there are not a lot of classical test data for interval methods. So we create some database which consists of 10 million objects and just 10, if I remember correctly, 10 parameters. And actually for that, in the computer, we need about a half of hour to construct patterns based on ordinal interval pattern clustering. For evaluate one of them, actually, I represent just one picture. It represents the average values of each object, including this data. So some practical examples, some example of practical projects in which we used these methods, different methods. The first example, we have some big project, some grant is called NF for Russian, some grants, and we tried to study state capacity. So we have some very big group of specialists which understand what is state capacity, very good political scientists, and we construct some. We need to separate different countries for countries with the same level of state capacity. But the problem here is a little bit hard to understand what is state capacity. So we know the definition of state capacity, one of the possible definitions, the ability of the state to perform basic functions. There are some basic functions, but in different papers, they propose different features for state capacity. So our group have a big discussion, say they propose this basic system of indicators. We have some colleagues, as I remember correctly, for USA, then proposed different parameters. So we discussed and we say that these parameters are good. So this is a result of correlation analysis. Of course, a lot of parameters are really correlated, and we try to use non-correlated parameters. As you can see, this data is not so big because we have just 5 parameters. This is our basic system of indicators for state capacity. The first, I'm so sorry. The first one, share of military spending in a country's GDP. The second one, share of military personnel in the total population. Number three, rate of tax revenue in a country's GDP. Some parameters which we call safety is parameter calculated at the inverse of the total level of homicides and victims of conflicts, and VGI indicator characterizing the quality of state institutes. So this example discuss which methods can we use, and we said that we can use pattern analysis and clustering, and then compare the results of these two methods. This is the first cluster which we constructed with really high level of state capacity. We have data for 60, not 60, for a biggest part of countries in the world for three years, 95, 2000, and 95, 2005, sorry, 2015. That's the result of the first pattern. In this case, when we compare the result of different methods of clustering and pattern analysis based on comparison parameters, in 98% we have the same result. So another result, as you can see, the level of VGI is a little lower here. Here, in 96% of cases, we have the same result for pattern analysis and clustering methods. So just example of different patterns which we have. And we have just one group of objects which cluster analysis combine and pattern analysis separate. Is groups like that. Actually, when we talk about this type of groups, we understand that the first pattern is just for countries with really high level of, not the first one, the last one, high level of oil and gas. So that's why we separate, pattern analysis separate. For clustering, we can combine actually. This depends what results we need in this case. The second example in which we use these methods of pattern analysis is when we study Russian regional innovation index. I'm sorry, this slide is in Russian because we use some Russian indicators, but we have a lot of indicators which represents of the level of science, the level of education, and the level of innovation activity in Russian regions. Sorry, just a moment. In Russian regions. So we constructed actually not 5 blocks, 6 blocks, but one is really correlated. And in our basic system of indicators, we had the first one block represents socio-economic conditions, the second one education potential, the third one the effectiveness of research and development, number 4 the potential of innovation, and number 5 the effectiveness of innovation. This result of correlation analysis, we excluded one block, so that's why we have 5 blocks. So this example for 4 different years, as you can see, we represent in parallel coordinates, then add in one set of objects every region, and automatically we can construct very fast patterns like that. The first pattern represent groups with high level of innovation activity: Moscow, St. Petersburg, and Primorsky Krai, so Primorsky region. So I very fast just will represent you some different groups of regions with the same level of innovation activity, education activity, and the same level, very similar level of science. As you can see, this structure in each group is really similar. That's why we can use pattern analysis methods. So the third example, using of which we represent methods of pattern analysis. So this, in this case, we studied COVID case. So I think everybody remember the pandemic times. So this is a representation of dashboard of Johns Hopkins University. They study the total number of cases of COVID, the total number of deaths, the total number of vaccinations, and etc. and we try to construct some model which predict the number of cases in each country, not in regional level, in country level. So what we try to do at first, we need some basic system of features. So we discussed different features, and we stopped with 4 main aggregated parameters. The first one, the intensity of separate quarantine measures. So the intensity, we can use the data of Oxford University of Oxford. The second one, number of infected people. We use the database of Johns Hopkins University. The education level, for education level, we can use the UNESCO data and some other data. And the last one is low epidemics. So this parameter with some, we talked with some experts, we set this low level of different countries. So low epidemics, what is that? To which extent people follow the rules stated by government. We have actually some criteria: school closing, workplace closing, cancel public events. So I think you remember all these criteria, and there are some grades. So for quarantine measures, so we create some one indicator. How can we aggregate this model? For that, we used actually threshold aggregation. What is threshold aggregation of quarantine measurement? It's a like graphic ordering of criterion values. So we compare countries pairwise by beginning for criterion with minimum values being equal 0. So what is threshold aggregation actually? For example, the country with parameters 212 is better than 303 because the second one have some minimum level, some critical level, some is 0. So a country for which the number of criterion with zero values is lower dominates a country with more 0 values. So if we don't have 0, 1, 2, and etc. For example, in this slide, we have the country 8 with average level of the first measure, average the second one, average the third one. And country B is taught, task, and mute. So country A dominates, in this case, country B. So, of course, we need to aggregate each methods. This slide demonstrates the method of aggregation. So we just aggregate by each day these measures. Just example in different countries. And we need to understand the number of infected people. What can we do? We use some method which is called, this method was proposed by Professor Alexei in different studies. So we try to use in the same method in this study. It's called LC course. So we need to construct some actually some like a function which represent the difference between the next time period and the previous one. And if we compare, use this pair comparison, we construct some line like that. And if the level is higher with this line, so the minimum will be higher, so we will have increasing level of infected people. In this case, we'll have decreasing level. So if we have something like a line, stable line, so we will have some stable level of infected people. Of course, the better is decreasing. So this is a formula. How can we construct LC curves? So for time series analysis of the number of infected people. Examples for some countries: China, Italy, Germany, and India. Some another examples. And why do we need pattern analysis and clustering here? We have some data, 66 countries, just complex data. We at first try clustering analysis, then compare with pattern analysis. Actually, the results was very similar, so we use both of them. This is some example from the 1st of February for 2020 to the 18th of May 2022. So we construct some group of countries, if we try to construct the prediction of the number of infected people for each country, the result was not really good. But if we construct group of countries with the same level of this, using just a moment, this basic system of indicators, the intensity of separate quantity measures, education level and low obedience, and then try for this group to predict the number of infected people, we actually have really good results. So for that, for predict the number of infected people, we need 5 time series. The best results is for 5 time series. More than 3, that's okay. Less than 3, that's not very good. So the example of different clusters, and for each cluster, we construct the some actually regression function which represent the number of infection people in each time. And we can use small prediction is just for 2 weeks. We have just 6 different patterns for 66 countries. And for that, as you can see, this is a representation of each countries. And as you can see, we have really good R squared. Actually, when we have this result first time, we think that we have actually something not very good because the results is really hard. But when we compare actually the actual results with the predicted results, we actually had we see that our models works actually in this case really good. So this is actually just very small example, but as you can see, more than 3 time series, the result is is good. More than 5 is will be not better. The result will be lower. So we use in each regression models, we use just 5 time series. These are results for our regression models. If we compare the number of weeks, for example, as you can see, for 1 week is for the first cluster is 0.5, not very good. But for 5 time series is 0.9, so really good result. We compare our results for different international groups, which the result they propose, and this result our result was really good. So another result for April 23 or 2022, where x squared is 0.8. And we have 20 more minutes. So the last theme which I want to discuss for my presentation is about reduction dimensionality in data. When I started this presentation, I said that nowadays we can collect a lot of data, and we need to do something with this data. After collect, we need to use some special methods for understand this data, for construct groups on this data. And of course, there are a lot of methods to reduction multidimensional data. The most famous, I think, is a principal component analysis, but it is not really used nowadays in really big data, what's called big data. But it's one of the most famous. If you have not really big data, you can use principal component analysis. The most famous and the first studied methods in universities, in a lot of programs of machine learning, when we start to study reduction dimensional data. So I propose the 5 one of the most popular methods in dimensional data. Ossenняя, now it's really used. Of course, expert analysis, when we can say which data you can use, which data you cannot use. Neural networks, really popular now. But we proposed some methods which we can use for reduction dimensional data when we talk about pattern analysis. For pattern analysis, a big problem too. So this is one possibility to use to exclude some parameters. So this method is based on some methods of political science, which are called power indices. In this slide, I just will introduce using terms on political science. Then let's introduce using methods, terms of pattern analysis. For political science, power indices are used for understand the power of each member of some parliament, for example. In this case, we have some set of parties. Each party have some number of votes, and we know the quota, the minimum number of votes which we need for make some decision. And we have two definitions for understand the power of each party. It's winning coalition and pivotal party. Sorry, I have a mistake, pivotal party. What is winning coalition? In some coalition, the number of votes of which is equal by the quota or more than the quota. So what is pivotal party? Is some party, if we exclude this party of winning coalition, this coalition stopped to be winning. So the number of votes of this coalition will be less than the minimum of the quota. And there are a lot of methods based on this definition. The most famous proposed in, as I remember correctly, 1965 is Banzhaf methods, really used for study. In a lot of studies, so for example, in about 3 years ago, there are some studies which represent the Banzhaf index in the biggest part of parliaments in the world. And we try to use the same logic for construct methods of reduction data. This logic is based on bands of distance. For bands of distance index, we divide the total number of cases, winning coalitions, where party I is pivotal, by the total number of winning coalitions where each party is pivotal. Very simple example, very fast example. We have some parliament for 3 different parties. The first have 50 votes, the second 49, the last one just 1. We want to understand the power of each party. At first one, we construct winning coalitions, A plus B with 99 votes. If the quota is 51, for example, for simple majority rule, A plus C with 51, B plus C is not winning, 50 is less than 51, and ABC. So the full coalition, so coalition included on all 3 countries, all 3 parties, sorry. And how can we relate? A is pivotal in AB, AC, and ABC in all 3. B just in AB, because in ABC we exclude B, A plus C will have 51 votes. They need just 50. They need 51 and they have 51. And for C, pivotal just in A plus C. In ABC, if we exclude C, AB will have 99 votes and the quota is 51. So that's why how can we relate using Banzhaf index the power of each party? Can we use the same logic in pattern analysis? Actually, if we see some example like that, we can understand that not a very simple example, a construct example just for features, and we can understand that not all not all features are important for us to separate 3 objects by 3 groups. So not all, obviously, in this case. Can we understand what features are important? Actually, what do we need to do? We need to say, okay, in terms of winning coalition, we will have some, in this sense, we propose not winning coalition, propose critical group and not quota, and not pivotal party. Pivotal party will have will be critical parameter. What is critical group in this case? Is some group of parameters using of which we can have the result which we need, the result in this case for, so we can separate for 3 groups. What is pivotal or critical in this case parameter? Is some parameter, if we exclude this parameter of some critical group, we will have different result. So the result will be not the same. So how can we use Banzhaf index? In this case, we propose some index. We just divide the number of critical groups where this parameter is critical. divide by the total number of critical groups where each parameter which we study is critical. Let's see on this example. In the first case, if we have the use just parameters a, b, which result will have? The first object will be in one group, we have some increasing, AB for the second case decreasing, AB the second case decreasing. So in terms of patterns, we will have two patterns. We need to do the same for AC. For AC, we have increasing, decreasing, decreasing. So we have two patterns here. And the same, for example, if we use BC, in all cases, we'll have increasing some piecewise linear functions. So we will combine all objects by one pattern. We need to compare, use all pair comparison like that. And for example, if you use A, B, C, D, all of them, we have separate the first one, the second one, and the third one. We will have three patterns. But as you can see, if we use just ABD and ACD, we'll have the same result. We separate by three different groups. So what's important thing here? ABC includes A, ACD includes A. If we exclude for ABD, for example, we will have the result of BD. The first objects and the second one will be in the first group, and the third one will be in the second group or the second pattern. So the result will be different. So for the critical critical group ABD, A is important. The same for example, ACD. A is important too, or critical in our terms. So if we divide the number of critical groups where this parameter is critical by the total number of critical groups where each parameter is critical, we can evaluate the importance of each feature. As we can see, the importance of A and D is higher than B and C. Let's check why. We have ABD and ACD, two small critical groups, smaller than ABCD, where we can have the result, the first object, the second one, and the third one. So we can separate all possible objects. So what is the important thing here? If we exclude A, B and D, and C and D, we'll have different result. If we exclude just D, we will have AB when we have the X1, so the first object, and for one pattern, the second and the third for the second pattern. But for ACD, we exclude D, we'll have just AC. We'll have the same result as AB. So A is important in this case, and D is important too in this case. But if we exclude B, for example, or we exclude C, with the same power, the same importance. We have AD, the result is different being ABD, but the importance here is higher, of course, with it's lower, sorry, with for A, because A is critical in the more case of critical groups. And that's it. We just studied some. We just started to start our studies about dimensional reduction. We tested this methods just in synthetic data. Synthetic data construct the same large with interval data, just 10 million objects, just 10 million objects, and just actually 20 parameters. Yeah, so the result is good, but it's not so fast because we need to use parent comparison. And then we are trying to construct some another method, the complexity of which will be smaller than this method. So method based on Venn index. So that's it. Thank you for your attention. If you have some questions.
Thank you very much, Alexei. It was really very, very nice presentation and very huge and very, let's say, deep understanding of these problems, which are really, and all this kind of applications also are very, very interesting and very important. Thank you very much. So questions, please. Alexei, You presented our work with concerning COVID, and I missed. Did you present also this very regression models concerning this infections, which we did in our one of our works?
No, we didn't present, Professor Leskerov. We didn't present it yet.
You didn't present. Okay. Because you see that's in fact, you see today there are some let's say specific ideas of World Health Organization that again you see new virus might come, etc., etc. And I think that our work really you see might be seriously helpful for this very situation. Okay, okay. Thank you very much. Some comments, questions, etc. No. Okay, thank you. And in 10 minutes we will switch to new presentation. Thank you very much, Alexei. Bye bye.
Thank you, Professor Alexei. Bye.
Okay, no.
Because you see, we don't have too much time, so to give you more time.
No, of course, yeah.
But I can tell about you half an hour. But
No. Please do not. No. Just 1 minute is enough. 1 minute is enough. So should I share my screen? Is it
yes,
possible?
please do it. Yes.
Okay, I will try to do it. I hope it will work.
Yes.
You can see my slides?
Yes, but change slides because sometimes it doesn't work.
Yes. It works.
Yes, works. Yes.
Okay, so
Good.
that's fine. Perfect.
Good. So now it is 12:02. Let's start. It's my great pleasure to introduce the next speaker, Professor Mishel Grabish from University Paris 1, Pantheon, Sorbonne, very good friend of mine, whom I know for many years. I was many times a guest of Pantheon, Sorbonne, and I would like to say that I do not like to talk too much, you see, not to take an important time of Michel's presentation, but I was always impressed the huge variety of topics which Michel covers in his works. So, and today, when I saw this very title of the presentation, I was really very much interested in what it will be. So, Michel, floor is yours.
Okay, thank you very much, Fuad. Thank you for the invitation. So I will try to give a kind of survey of on the topic of the random generation of capacities. So let me explain first what I mean by capacity. So it's simply a monotone set function vanishing on the empty set. So for those knowing TU games, cooperative games, it is nothing more than monotonic games, like, for example, voting games.
Sorry, Michel, just we can interrupt during the talk.
Yes, sure. Anytime you want.
Monotone in terms of the cardinality of the set, you mean?
Monotone in terms of the inclusion. So
inclusion. Okay.
Yes.
Yeah.
So if A is included in B, then the function for A is smaller than the value at B. I will give later the definition, of course, mathematical. Okay. So it is used in operation research, decision making, because it is seen as a non-additive probability measure. So instead of additivity, you have just monotonicity with respect to inclusion. This is the meaning. This is also used in combinatorial optimization. So there are many, many fields where capacities are used. And an important issue, if you do some machine learning, optimization, and so on, is how can you randomly generate capacities in a uniform way? So the question looks extremely simple, but as I will explain, it is in fact a difficult problem. The theoretical solution is known, so that's good, but in fact it is intractable. As soon as you have 5 elements in the universe you are considering, so it's very, 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 very limited. So you need some approximation method. We will see some of them. Let me explain about possible applications. So as you will see, most applications I will present are in the domain of multi-criteria decision making, because a capacity can represent the importance of groups of criteria. So what is well known in decision making is that you can put weights on individual criteria, and then you take a weighted arithmetic mean or a weighted geometric mean, and so you get an overall score for each alternative. But there is a more subtle and more flexible way where you put weights of importance not only on individual criteria, but also on groups of criteria, pairs, triples, and so on. Okay. Then you can model many, many behaviors in decision making, like veto criteria and things like that. And this is done through capacities, and then instead of the weighted arithmetic mean, you use a shock integral. So this is an extremely brief summary of why we use capacities in decision making. Okay. So now in this context, there are several possible applications. The first one is typical machine learning. Because in many optimization algorithms, especially meta-heuristics, you need an initial population to start your optimization. An initial population should be as fair and diverse as possible. It means that you have to you need uniform population of capacities. So this is the first application. Second, which is very important, robust recommendation. This is a well-known method in multi-criteria decision making. Most of the case, there is not a unique capacity representing the preference of a decision maker, but there is a polytope of capacity, so infinitely many. And it's important to know what would be the ranking of the alternatives when all these capacities in the polytope are used. So this method is able to tell to which percentage alternative number 7, for example, would be ranked as the best alternative, and so on. So for this, you need to generate uniformly capacities. Third application is related. The preference of the decision maker are elicited one by one, and each time you reduce the polytope of compatible possibilities, capacities, sorry. Capacities which are compatible with the preference of the decision maker. Number 4, it can be used also as a benchmarking for various elicitation methods. Then you can simulate a decision maker, and for this you generate one capacity, and this represents a mental model of a decision maker. Okay? But in order to do this in a fair way, you should use a uniform a capacity which is randomly generated, but in a uniform way. So there are many cases where this is useful. So after this introduction, we can dive into the topic. So you see that my presentation has 6 parts. Not sure I will be able to explain all of them. So let's start with the first one, explaining what is the problem of randomly generated capacities. So first, I introduce the basic definition so as to make clear what we are speaking about. So I consider a finite universe n of n elements. And I recall that a set function on n is just a mapping from the power set to the real line. So to each subset of n, you assign a number. Okay, so now what is called a game, TU game, is just a set function which satisfies this property. V of the empty set is equal to 0, so nothing else. And now a capacity, in addition to satisfy this property on the empty set, should satisfy what is called monotonicity, and here is a definition. So V of S, ST are two subsets of N, S is included in T, and then V of S should be smaller than V of T. So for example, a probability measure satisfies this property. So a probability measure is a capacity, a particular one, very particular, of course. You have also belief functions and so on, a lot of examples. So sometimes we will need to use this notation, C of n, the set of all capacities on n, because this set is defined by linear inequalities, which are here. So it's a polytope. The dimension is 2 to n minus 2 because V of n is fixed and V of the empty set is fixed. So you have 2 dimensionless, and that explains this number. Okay. So, but so it's not only a polytope, it is a special type of polytope, which is called in combinatorics order polytope. I will explain this in the next slide. So now we explain more generally. We take any finite poset, that is to say a finite set, endowed with a partial order, that is to say reflexive, antisymmetric, and transitive. Okay, so for example, of course, the typical example is a power set with inclusion, set inclusion as a partial order. This is a good example. So now an order polytope, or the order polytope associated to the poset P, is the set of function f from P to the interval 0, 1, such that the value of f follows in some sense the order of the poset. So if x is smaller than y in the poset, is below y, then f of x should be smaller than f of y. There is no other restriction. Okay, so this is called the order polytope, O of P, of the poset P. Then it is a polytope, of course, because it's defined by linear inequalities. Dimension is P because all variables are free. And so the next important topic, notion is linear extension. So again, you consider a poset P with some partial order, and a linear extension is simply a total order on P, which is compatible with the order of the poset, which means that if x is below y in the poset, then in the total order, in the linear extension, X is ranked before Y. Okay, so we can imagine a linear extension as a permutation. So if P is a poset with P elements X1, XP, okay, then a linear extension corresponds to a particular permutation such that yes, so you denote by sigma 1 the first element you take, and by sigma p the last one in this total order. Okay. So now for notation, set of linear extension of p is denoted by E of p and small e for the cardinality. So I think you have noticed the similarity between the definition of a linear extension and of the order polytope is same, in fact, because x smaller than y implies f of x smaller than f of y. And here you have x smaller than y implies x is ranked before y. So they are closely related. So there is no surprise that, in fact, each linear extension define a region of the order polytope. It corresponds to a certain set of function f, which ranks value, which ranks the element of p in this way. Okay, so exactly in the same way as linear extension, because remember x sigma 1 is the first element, x sigma 2 the second, and x sigma p the last. So now, since f is a function in the interval 0, 1, so if you consider all functions mapping to 0, 1, from P to 0, 1, then it is a hypercube of dimension P. And the hypercube, as you know, can be divided according to all possible permutations. So each permutation defines a region in the hypercube. They are all identical. And so the volume of such a region is simply 1, which is the total volume of the hypercube, divided by the number of permutation, which is factorial p. So,
Michel,
yes,
sorry,
yes.
sorry. Because you see, I did some works concerning this linear extensions.
Yes.
Can we say that these very linear extensions might be represented? You see, I never thought about in geometrical sense.
Yes.
That there are planes inside the polytope.
What did you say? Yeah. Can you repeat?
Plane.
Ah, planes. So inside the
inside the polytope.
Yeah, but inside the order polytope, they define regions.
Yeah, region, but they might be represented as planes, no?
So the planes are then the frontier between two such regions, to my opinion.
Well,
it's like
maybe it goes out of your talk. Sorry.
No. No, but I think there are several ways to look at linear extension. So sorry, I have no figure for this, but yeah. So what is important is to understand that each such region has the same volume, which is 1 over factorial p. So the vertices we don't need, so I skip. And they define a partition of the order polytope. Yeah. And then we can compute the volume of the order polytope. It is simply the number of linear extension multiplied by the volume of each region, which is 1 over factorial p. So we have the volume of the order polytope. Okay, so these are the general facts valid for any poset. Now we apply this to our case, which is capacities. So let's see what. No, so this is a little bit later. So now, based on the above facts, you can uniformly generate a point in the order polytope. Remember, so the order polytope is a set of functions. So to pick at random a function in a uniform way, it amounts to uniformly select at random a linear extension, because then it selects a region. They have all the same volume, so you just pick one of them, okay? And then when you are in this particular region, you have to pick a point in it uniformly. So, and to do this is easy because you just generate p numbers in the interval 0, 1, which are candidate values for the function f. You order them in increasing order from z, that's, let us say z1 to zp, okay? And then you say z1 is the value of f at x sigma 1, and zp is the value of f at x sigma p. So remember, sigma is determines the linear extension. And so it is simple. So this is a general way to uniformly generate a point in an order polytope. And fortunately, the set of capacities is an order polytope because the underlying poset is simply the Boolean lattice, the power set, minus empty set n. Why? Because simply for this set, the value is already fixed. The capacity should be equal to 0 for the empty set and to 1 for n. So this you can discard and you consider the rest. And it is easy to see that a capacity is indeed a function because it preserves the inclusion relation. If S is included in T, then F mu, or let us say mu for the capacity, mu of S is smaller than mu of T. So the set of capacities is the order polytope associated to the Boolean lattice of all subsets of N. And for this reason, it is so first we know the volume of the set of capacities. It is simply the number of linear extension of the Boolean lattice divided by factorial the number of elements. But the number of elements of this Boolean lattice is 2 to n minus 2. So so let's see the numbers behind of it, because everything looks now simple. So volume can be computed. Since it is an order polytope, now random generation is solved. You just apply the method on the previous slide, and that's it. But there is a big problem, which is given in this table. This is a number of linear extension of the Boolean lattice. So 2 to n or 2 to n minus empty set n gives exactly the same number. So you see that the number of linear extension is growing so fast that it is totally impossible to generate them. So it's possible to generate all linear extension for till 4 elements, n equal to 4, but then it becomes too big to be simply generated. And even more, the problem is, yes, yes.
We should learn how to convert these numbers into cents, at least.
Into?
Cents, not in
cents.
euros.
Yes, absolutely. And the other problem is, so this is a well-known sequence we can find in the online encyclopedia of integer sequence. This is the number of this sequence. It is not known beyond 7. So the exact number is even not known, and only some bounds are known. This is a reference where you can find this. So you see, there is becomes intractable. So the theoretical perfect method is intractable as soon as n is equal to 5. Now let's look at the volume, because we were able to compute the volume of the set of capacities. This is also amazing, because it goes so fast towards 0 that it is very bad news. Because what does it mean? Suppose you want to generate a capacity with n equal 5, so 5 elements. Okay. Then it means that if you randomly generate a point in the hypercube, then you have absolutely no chance to find a capacity, because the volume of the hypercube is 1 and the volume of the set of capacities is so tiny that you have absolutely no chance to find one. So you absolutely need some serious method to find capacities. Okay. So this is just a summary of how to generate in theory a capacity randomly. So you select, so I summarize, you select uniformly at random a linear extension of the Boolean lattice. So it is a collection, a collection of sets. Okay. This defines a region. So it means that in this region, every capacity V satisfies these inequalities. And this would be the set with the smallest value, and this is the set with the highest value. Okay. Then you generate 2 to n minus 2 numbers in 0, 1, and you assign this now. You put them in increasing order, and you assign this number one by one to these sets in respecting the order, and that's finished. So, but not feasible as soon as n is equal to 5. So if we speak of exact methods, so the first exact method follow what I just explained, and you just have to generate all possible linear extension using, for example, a depth first search algorithm. This is quite easy to do, but it's doable only if you limit to n equal to 4. But there is another possibility which permit us to go to n equal to 5, which is not possible via the first method. So now I will explain the second method, which uses the lattice of ideals. So I have to explain what it is. So let's see what it is. So I recall that if you have a poset P with some order, an ideal of the poset is a subset D of P, such that if you take X in D and Y in P, which is below X, then Y must be in D. So it's also called the down set. So it means it's something like this. If you pick an element, then all elements which are below must be included into this set. Okay, this is a set. This is an ideal. So now this is well known, but just to recall, a poset is a lattice. If picking two elements, their supremum and infimum exist. And the lattice is distributive if infimum and supremum obey distributivity laws. So what is known is that the set of all ideals of a poset, denoted by O of P, endowed with the set inclusion, is a distributive lattice, which is called the lattice of ideals. So maybe the best is to see an example. Let's take again the Boolean lattice with 3 elements only. So, and you discard n in the empty set. So this set has 6 contains this set contains 6 subsets, yeah, which are denoted by 1, 2, 3, 1, 2, 1, 3, 2, 3. These are the subsets of 1, 2, 3, let us say, okay? So, of course, the set itself is an ideal because it contains everything, and the empty set is the other trivial ideal. Now, all other ideal I represented on this figure. They are ordered by inclusion, as you can see, and this form a distributive lattice. So just to pick one, let us pick this. So this is an ideal because the subset of any set in the ideal belongs to the ideal. For example, if I take 1, 2, the subset of 1, 2 are 1 and 2. They belong to the ideal, so it's correct. This is another example, and so on and so on. Okay. Now, what you can see also, if you go from here to here, so then you add a new element, which is 3. Or let us take another, taking another example here. If I am here, I go here, I add a new set, which is 2, 3. And as you can observe, the subsets of 2, 3, which are the singletons 2 and 3, belongs to this one, which is called the successor of this one. So going into this direction, you get the successor, and going in the upper direction, you get what is called the predecessors. So this is explained on the next slide, successor, predecessors, okay, exactly what I said. And also this I explained on the example. If you take two ideal D prime is a predecessor, so it's above, okay. Then the difference between these two ideals is a singleton of P, so it is, in our case, a set, such that all predecessors belong to D. This is what I said before. And so the consequence of this is that if you consider a path from the empty set to P, then you get a linear extension. So let's see this instead of explaining this by formulas. Let us see this on the example. So a path from empty set to the top. So for example, you can consider this path. Okay, it's called also a maximal chain. So look, so then the first one you get is 1. Then the next one is 2. Then the next one is 3. So 1, 2, 3. Okay, this forms the beginning of a linear extension. Then you go here, for example, and you put 1, 3. And 1, 2, 3, 1, 3 is indeed linear extension. Then you go here, you add 1, 2, and then you finally add 2, 3. And so any path from the empty set to the top defines a linear extension, and conversely, any linear extension must be a path in this lattice. So the trick is that consider n equal to 5. N equal to 5, the number of linear extension is tremendous. You cannot represent it. But the lattice of ideals is still of manageable size. So you can draw this picture for n equal to 5. And then any linear extension is just a path in this lattice. That's the trick to go till n equal to 5 for a generated linear extension. But how does it work then? Because you cannot generate all of them. There are too many. So what to do? But you should simply generate some of them randomly, but randomly with right probabilities, of course. And this is done via the figure which is here. So what is this figure? This figure explains how many paths you have. For example, let us take this this node corresponding to this ideal. Okay, it is written 2. It means that to get here, you have two paths. This is the first one, and this is the second one. To get here, you have 2 paths. Okay, to get here, you have 2 paths. So if you go here now, you have 6 because it's 2 plus 2 plus 2. If you are here, you have only 2 because this is the only way to go from here to here. And here you have 8 because you have 2 plus 6, and so on. So the number of linear extension for n equals 3 is equal to 48. So thanks to this trick, you can have at any node the number of linear extension for the corresponding poset. Yes. Okay. So then let's see. Then you can use this method to generate uniformly at random a linear extension. You pick a maximal element with a probability corresponding to frequency of occurrence in the set of all linear extensions. So again, it's better it's explained with a figure. So, for example, so of course, maximal elements here, there is only one. So all linear extensions, they finish by this. But now, consider this second maximal element if you delete this one. So you see that there are as many linear extensions finishing here or here or here. There are 16 exactly. So equal probability. But if you go down and down, then it's no more always equal. For example, here, you have only 2 linear extensions going here and 6 here. So you have probability much higher to pass through this node. And so you take this into account when generating the linear extension.
So, Michel,
Yes,
sorry.
any question? Yes.
Yes, just to understand. So when you construct this very path, you take into account these numbers as in a sense, more preferable to go by 6
Yes, exactly.
rather than 2, right?
Exactly. That's right.
Great.
That's right. Because the problem you see, when you take n equal to 5, the lattice is so big, the number of maximal chain is too big, and you cannot generate all linear extensions. So you select at random. And for this, you need to know the probabilities. Yeah. So this is, yes, what I wanted to say about exact methods. Now we go to approximate methods. So there are some, so I listed the most famous one. First one, random node generator. We will see this in a moment. Second famous method is the Markov chain method. We will see this in a moment. And then there is a variety of several methods. We will not detail because it is too much. To take too much time, but there is an abundant literature on this you can find. Okay. So now maybe I explain the first one, the random node generator, because this is something very simple. So this is the algorithm. You see, it's very short, very simple. And again, so I prefer to explain with an example. It will be better. So let's go immediately to the example, which is here. So on the first figure here, you can see the Boolean lattice of all subsets of n with 4 elements. So this is the empty set. This is n with the 4 elements, and all subset of 3 elements, 2 elements, 1 element, so the singletons. Okay. So now the method consists in the following. Of course, you fix the value 0 for the empty set. You fix the value 1 for n. This is, of course, no choice. And then you pick at random any set. For example, this one here with a black dot. And then you generate a number in the interval 0, 1. Why 0, 1? Because this number must be smaller than 1 and bigger than 0, of course. So you generate, for example, 0.65. Okay, why not? Then you pick another subset, let us say this one, and again you generate a number uniformly in the interval 0, 1, because there is no special constraint on this number. Okay, then you find 0.41. Okay, why not? Then you pick a third one, this subset. But here you must be careful because this subset is included into this one. So the value you will generate for this one must be smaller than 0.65. And so instead of generating a number in the interval 0, 1, you generate a number in the interval 0, 0.65. And you find, this, for example, this. And you continue like this. Each time you select a new set, you look at the possible constraints coming from supersets and subsets, because you must generate a number in the interval imposed by the all supersets and all subsets. And then you get this finally. So it's very fast, very simple, but as you will see, very bad. So it gives very poor results. We will see this later. So this is the first method. Now the second method, the Markov chain generator. So again, it's a very general method. It's not only for capacities. You can take any poset with any order, finite poset, of course. And this method generates linear extensions. Okay. So we say that two linear extensions are neighbors if they differ only by a single switch, let us say switch. So for example, you take linear extension sigma, this is the order, and then you switch the two elements here with order k and k plus 1, and you get another linear extension tau. Supposing that it is indeed a linear extension, of course. If you switch any number, maybe it will not give. If you switch any two position, maybe it will not give a linear extension. Okay, so it's not automatic. So these are this is definition of two neighbors linear extension. So now this gives you the transition matrix. So you have a probability of going from linear extension sigma to linear extension tau if either they are neighbors or they are the same. Otherwise, there is no probability of transition. Okay, and the probability of transition is designed in such a way that, of course, the sum is equal to 1. And so, roughly speaking, you have 1/2 probability of the number of neighbors, of possible neighbors. So this is proved to be an ergodic time reversible Markov chain and converging to the uniform distribution on EP. So this, I forgot to say, of course, the set of states is a set of linear extension. And there is only one absorbing class, which is the class of all linear extension. And the probability at asymptotic probability is uniform. So if you run this Markov chain enough time, enough long, then you get a uniform generator. So the method is asymptotically perfect, but it is only asymptotically. So this is the algorithm, no need to define more, detail more. So now let's, so any question? Yes, yes.
Sure, sorry, can you go back?
Yes. This.
Here,
Yeah.
N of sigma is the number of neighbors.
No, of, yes, yes,
right?
yes.
So it is p minus 1
At most.
because of the ranking. So it is minus p minus 1. It will be 2 minus p, right?
So if the number of, yeah,
p
if the
is
number,
p is equal to 3, for instance, might it be that if we get this sigma is equal to tau, that might be negative values there?
No, because n sigma is at most equal to p minus 1. So
yeah.
this is at
so
at least one half.
If p is equal to 3, it will be 2, right? P minus.
Yes.
Then n of sigma is minus 1, right?
2, yes. Yeah, and so, but it cannot be negative then.
It cannot be negative.
No,
yeah.
because this is smaller than 1 always. It's smaller than 1/2, in fact. So this is bigger than 1/2. So it means that most of the time you don't change.
Yeah.
And sometimes you change.
According to the Markov chain,
Yes.
I understand that it shouldn't be negative, but maybe
yes.
something is misprinted there. Okay.
Sorry. Sorry.
Okay. Well, you will look at this after.
Yeah. Okay. Sorry if there is a misprint. So I can continue.
And what is interesting that it is a theorem, yes. This further Markov chain, very interesting theorem.
It's very. It's this is was let me see, Karzanov and Khachiyan, 1991.
I see.
This is a very good paper. Yeah, it's published in order.
Khachiyan, I met him a couple of times. Yeah.
Okay. So this is they have produced this paper which is fundamental in the generation of linear extensions. Yeah.
I see.
Yeah.
Okay.
So let's go further. So next method, maybe I will not speak too much about it because time is flying. So 2 layers. This is a method we have proposed. How to explain it simply, because there is a lot of things here. So basically, the principle is the same as the lattice of ideals, in the sense that you don't generate all linear extension, but only you sample, and you try to sample it in a uniform way. So that is to say, you have to pay attention to the probabilities of selecting with the right probability a maximal element or a minimal element. Let's see this on an example. So our idea was to, in order to avoid the complexity of big posets, so this is a full algorithm, but no time to explain. Let's see on this example. Our idea was to, in a poset, so this is a poset for 4 elements, okay, n equal to 4. So you see all subset of 4 elements, except empty set and n itself. And then you select the two first layers, that is, this gives a name to the method, the two-layer approximation, to select a maximal element, and then the two bottom layers to select the minimal element. So, and you do this in each step. So, for example, at first step, you have 4 maximal elements which are in red. So you select one of them, let us say this one. And to select, then you have to compute the probabilities. And you have a formula for this, which is rather complicated. And then select this. And then you select a minimal element from the two bottom layers. For example, you select number 1, and then you get the figure C. So each time you select, you destroy this element. So the poset is changing, okay? Here, there one element less here, one element less here. And then again, you select a maximal element in the upper layer, in the two upper layers. For example, 1, 3, 4, it disappears, you see? And then you select a minimal element here, for example, 4, and then you get this figure. And so on, you continue till you get only an untied chain and no more order relation. Okay, you get this. And then what you have selected one by one, you form the linear extension. So you put, remember, first you have selected 2, 3, 4. This will be the last element in the linear extension. And then we have selected 1. This will be the first. And then we selected 1, 3, 4. Last but 1, and then 4, it will be the second, and so on. You continue like this, and the sets in blue in the middle, they are these sets, because then you can order them as you want. There are 5 factorial 5 possible orders for them. And so you get like this a linear extension. The only thing to do is to select your min and max elements with the right probabilities. So as you can see, the right probabilities are rather complex to compute, but it's something which can be done. So let's see, without further delay, the results, experimental results. So let's see these histograms which are produced by the exact method. So we are with n equal to 4. And so with n equal to 4, you are able to produce all linear extensions. And so the method is perfect. And if you do this, you get this histogram. So on the first row, this is a histogram of the value for singletons. So all histograms are identical because it can be proved that distribution with same cardinality is the same. So you get this for the singletons. For the pairs, you get these 6 histograms which are exactly the same. So these are the distribution of values for pairs. And this is a distribution for triples. Okay, from 1 to 3, 1 to 4, and so on. Okay. As you can see, they are symmetric from this one. It is simply the same, but just flipped. Okay, so this is the exact distribution. Now let's see what produce our method. So as you can see, small difference, but it's almost the same. Okay, so good. It is a good approximation. Now let us see what happens with the Markov chain generator. Then you get also something which is very close to the, this is the exact distribution. This is a Markov one, it's almost the same. Okay, so it's Markov chain is a very good method. So now this is what is generated by the first naive method, the random node generator. You see that the histograms are quite far from the real ones. So this shows that this method, which is very fast, is extremely bad and should not be used. It's not at all uniform. Okay. So yes, you have a question?
Opposite. No, I'm really surprised. You see, random node generator. I didn't think that.
It's terribly bad. Yeah.
Terrible. Yeah, really terrible.
Yeah, absolutely.
Fantastic.
So let's see now the computation times. Compare our two-layer approximation method with the Markov chain. So as you can see, we are much faster. It is more than a factor 10. It is increasing, in fact. And so we have selected T is the number of periods you run the Markov chain till reaching it is a mixing time, okay? And we have determined the mixing time so that the precision of approximating the exact distribution is the same, is similar, let's say. And said to get a similar precision as ours, you need, for example, you need 500,000 periods to be mixed. Yeah. And so it takes a long time, and this shows that our method is quite good to generate capacities. So now the next one is how to improve the random node generator. So you remember the results are very bad, but why are the results bad? Simply because you, when you select a number, you select it uniformly in some interval fixed by the monotonicity constraint. And the problem is that the probability of mu of s is not at all uniform. So we have tried to analyze this, so it's a bit difficult. So I have the full explanation here, but maybe I will not detail too much. Let us just start with it and we will see. The fundamental fact is the following. This is a starting point. If you take m numbers which are generated by identically distributed and independent random variables with uniform distribution in 0, 1, the case number, when we rank them, okay, follows a beta distribution, and this is fundamental. This must be the starting point of the method, in fact. So now consider I select a set subset S, and I want to generate a value for this set mu of S, okay? Then I need to know the rank that S will take in the linear extension. We denote this by rank of S, okay, like this. And of course, the rank of the empty set is always 0. The rank of n is always maximal 1, of course. But for the rest, we don't know. So now, if you want to compute the cumulative distribution function of mu of s, then you just condition with respect to all possible ranks. So it is probability that mu of s is smaller than some x, given that the rank is equal to I, multiplied by the probability of having this rank, and you run I from minimal possible rank to maximal possible rank. So this is the first formula. Then you have to compute these ranks. Yes, but what we do in this method is more complicated because don't forget that you generate the value one by one. So imagine you have already selected S1, S2, and 2 SP. You have generated the values for these sets, A1, AP. And so as you remember from the, let us show the figure to be more clear. So as you remember from this figure, the more you generate, the more you have constraints on the new one you want to generate, okay? And so you must take this into account into your computation, sorry. Try to, yes, so, and now this imposes constraints on the value of mu of s. There's a minimal value, maximal value, this is easy, but there is also a constraint on the rank. The rank of S is now more constrained than before. And it's not so easy to compute the good value for the rank. So let's skip the details. This is the formula for computing it. You see, it's not so easy. And then, yes.
Sorry. This very formula came from beta distribution?
So these considerations are outside the beta distribution.
Outside, yeah.
Yes, outside, because see, you have to determine what is the rank. When you know the rank, then you use the beta distribution. But if you don't know the rank, then you cannot do anything.
But the rank is defined by.
Yes, so you
by okay.
It depends on the value you have already generated before.
Yeah.
It constrains more and more.
It's a sequential procedure. Okay.
Yes, sequential, exactly.
Yeah.
That's why it's a bit complicated. So this is final formulas. Maybe let's keep this difficult to explain. Let's see the result. So we compare the performance of our improved random node generator with the Markov chain generator, which is considered as a benchmark, using the Kullback-Leibler divergence, which gives how much different are the distributions. Okay, so let's see first the result on the histogram. So you see that what you obtain, if you remember the exact distribution, is almost the same as the exact distribution. But let us do something more quantitative. So this is Markov chain. So in principle, it's better. So here is a table giving the Kullback-Leibler divergence. So first line, so we have three tables, because one table for the singletons, one table for the pairs, and one table for the triples. Okay. First row is a random initial classical random node generator. Second row is the improved version. And third row is the Markov chain. Of course, the Markov chain gives the best result. This Kullback-Leibler divergence is very small. With our method, with the improved generator is bigger, to a factor, let's say 3 to 4, but it's 10 times better than the classical random node generator. So it's much, much better than the initial method. You can check this on any part of the table. So now let's look at the computation time, because this is also important. And then this is the result. So result for a set of 4 elements or 5. What we see is that the random net generator is very fast. You need 1 second to generate 10,000 capacities. But our improved version, of course, is much slower, but still reasonable, and compared to the Markov chain generator, when you need 100 times more time, in fact, compared to the classical random node generator. So I think it's a good compromise, because you don't have the precision of the Markov chain generator, but it's enough good and very fast. So yeah, I think it's a good result and a good compromise. So let's go to the last part, which is not so too long. Now, what happens if you put more constraints? You don't want something uniform, but no, you want something uniform, but now it's you put some preference information. So this is important, because if you do some decision making, of course, you have always a decision maker, which will give you some preferences. Okay, so for example, if the decision maker says that A is equivalent to B, is indifferent with B, then the value computed by the Choquet integral of A should be equal to those of B. And if A is preferred to B, then the value for A should be greater than the value for B, of course. Yeah. And now we want to generate capacities compatible with these constraints. So I don't give the definition of Schoch integral, but you can check that such constraints induce linear constraints on the capacity. And so you must add this new constraint to the monotonicity constraint. So let's maybe give an example. So the naive method is to say, okay, just generate capacities randomly with our generator, and then keep only those satisfying these inequalities. This is fine. This is acceptance rejection method, but the acceptance rate can be quite low, less than 1%, and then it's not no more feasible, no tractable. So let's see an example here, a real one. 6 alternatives. These are the scores and the criteria. The decision maker says that A5 is better than A2, which is better than A3, and A6 is better than A4. This gives you 3 constraints on the value taken by the Schoch integral, and so 3 constraints on the capacities. And if you compute the corresponding volumes of the polytopes, this is the volume of all possible capacities is given, it is this number, and the volume of capacity satisfying these 3 inequalities is only this value. So it's 10 times smaller. So the acceptance rate is only about 10%, 9.7, okay? So it's still reasonable, but imagine you add more constraints, and this value will drop to 1% or 0.1% and so on. So it's no more feasible. Yeah? So what we see, so roughly speaking, so what we were able to do is to take into account 2 types of constraints. This one, so μs is smaller than some μs prime plus something, or μs is smaller than some numerical value, something like that. More complex, for example, 2 mu of s minus 3 mu of s prime greater than 3, this we cannot do, okay? So which means that we cannot represent exactly this kind of constraint. So we must, this is an approximation. In fact. And what we do, as I will explain, is that we approximate by these constraints preference information. So, but what we were able to do is that by modifying the definition of this, it's possible to incorporate these constraints into the random node generator we explained before. So, so let's see how we do that. What we do is we take all our constraints. These are the preferential constraints, okay? And these are the monotonicity constraints. And then given this, we look for the minimal value taken by subset S. So it's a linear program. We solve it and we get the minimal value. We do the same with the maximal value. We do the same with minimal value of difference of 2 subsets, maximal value. And so we get all constraints of this type. Okay, but we have to solve a great number of linear programs. And then we will get this constraint. Let us illustrate this on an example. So exactly the same example as before. So with 3 criteria, then we need to solve 42 linear programs, and then you obtain this system of linear inequalities, which are of the type SC, so the type we are able to handle. And of course, this defines a polytope bigger than the real one with the real preference constraints. But the volume of this polytope is this value. which is 3 times bigger than the polytope defined by the true preferential constraints. So it means that we have still an acceptance rejection rate of 0.3, but this is much better than 10%. We have
It's
37.
almost
Yes.
It's almost 4 times better.
Yes, yes, almost 4 times better. Yes, you are right, not 3 times. Exactly. So it's an improvement, and of course, generating a capacity now is longer. So you have a trade-off between reducing the augmenting the acceptance rates, but not too much computation time for one step. So
Mishel,
yes,
sorry, is it with including these linear programs also?
Yes, good question. No, it does not include it. I don't think so, because you do this once, and then you generate as many as you want.
Yeah, I understand.
But you solve the linear programs only once, and then you, yeah. So I don't think it's
for a fixed number, you do it once and just incorporate inequality.
Yes. But since now the algorithm is more complicated, it takes more time to compute to generate one capacity. That's why yeah. So here is another example with 4 criteria and more constraints, and you see that if you add only one constraint, then it's not interesting. The computation time is longer with the revised method, but the more you add constraints, then it starts to be interesting, because then the rejection rate is too high, and then you spend a lot of time for just rejecting the capacities you have produced. So this is what we have obtained. So now it's the end of the talk. So I explained that random generation of capacities is an important problem in machine learning, especially in multi-criteria decision making. Exact methods are tractable only till 5 elements, 5 criteria. The Markov chain yields something which is perfect asymptotically, but takes a long time. We have proposed 2 methods which are quite fast and give very good results. And if you want to incorporate preference information, this is not so easy, and still more research is necessary into this direction. So this is a list of references. So 2 articles we published recently. And these are the reference for the lattice of ideals method, the reference for the Markov chain method, and the reference of the random node generator. Thank you very much for your attention.
Thank you very much, Michel. You see very impressive work. And, really,
Thank you.
Enormous number of applications, you see.
Yes, I think.
I know a lot of cases when we need these linear extensions.
Yes.
So,
absolutely.
sorry. Please, questions, remarks, comments, and there is a question from. I told you that there is another network also who listen you. A question on machine learning applications. Could you comment a bit more on application of capacities for machine learning purposes? When and how it can be applied? Maybe you say a few words about it.
Yeah. So the application I have mentioned is all about multi-criteria decision making. So this was the emphasis. But I think you can find other, because I think purely in machine learning, with many methods like genetic algorithm and so on, you need to generate an initial population. If you want to train your machine or capacities, then initially you have to produce initial population of capacities. And this is difficult because to produce them in a uniform way, it's a problem I have explained, and it is difficult. And I think that many people do not suspect it is a difficult problem, in fact. So this is very general and not limited to decision making. So you can use to combinatorial optimization or something like that. Yeah. Or voting theory of maybe this, I don't know. See, I have not investigated into this direction, but could be also interesting.
Yeah, there is a series of works in voting theory. I don't know them well, but concerning this this type of single peak preferences, etc.
Yes.
To choose this kind of things, you see.
Yeah, maybe
to
it
generate
could be
profiles.
interesting. Yes. Absolutely.
That might be very interesting.
Yeah.
Okay, good. Some other questions? I'm sorry, I asked all questions during your talk.
No. Of course, this is good.
Yeah. Some other questions, comments, remarks, please go ahead. No. Again, thank you very much, Michelle. It's really, you see, very impressive work.
Thank you very much. I am glad that you liked it.
Very impressive. So we stop then now, and sorry. And next our today's talk is will be at 5 o'clock. So please join. Okay. Michelle, tell my hello to Agnieszka. And
thank you very much.
And I'm waiting from you these materials. Okay.
Yes, I have understood. Thank you very much.
Thank you.
So I stop.
Bye bye.